My pleasure to introduce Yasaman Bahri from Google Brain, and she's going to talk today about understanding why deep neural networks and their relationships with GPs.
Can you hear me? So thank you very much to the organizers for the opportunity to give this talk here. I wanted to apologize in that this is mostly a survey talk, a little bit about older work and some more recent stuff. So it will be known to a certain subset of the audience, but I hope there's at least a different subset for whom it will be new and worthwhile. So the work that I'm going to talk about today, the various papers are all done with subsets of mostly of these people who are my primary collaborators at Google Brain, very great researchers, all of them. And so the outline I have for the talk today is that I just want to start off with a little bit of motivation, maybe a little bit of philosophy as well, and then go through these various topics. So the very first one is now a paper from last year, which makes the connection between infinitely wide, fully connected deep networks and Gaussian processes. I want to take a little bit of a tangent and talk about the relationship to a different line of work that might go by the name of signal propagation, but it's very much closely related to the same sorts of analysis of the same sorts of structures that appear here. Then I'll come back and talk about the correspondence between Gaussian processes and convolutional deep neural networks. Up till this point, it'll all be about Bayesian inference, but then we'll talk about gradient descent with some more recent work, and then I'll close. So this is maybe one slide of a little bit of philosophy about how to approach deep learning, coming maybe from a perspective taken from the theoretical sciences, or at least my own perspective. So neural networks seem like they're complicated systems. Where do you start understanding a complicated system? So there's what you need is a very tight feedback loop, of course, between theory and experiment. Maybe one point I just want to say about experiment is that enough experiments need to be done so that you identify the phenomena which are prevalent enough, maybe semi-universal, if you'd like to call it that, that would warrant an explanation. And this is maybe just a minor point at this stage, because deep learning is so open that a lot of the big questions are still the big questions. There are big questions that are very obvious that we still haven't answered, for instance, generalization or training dynamics of very nonlinear networks. But maybe looking further ahead, there are, at some point when a field starts to develop, and a lot of the very basic questions start to be answered, what becomes hard is to identify kind of what are the other right questions to answer, and some of them can sometimes be too microscopic. So one example I want to give is maybe one time a practitioner asked me why, if he were to go and replace, a particular layer of a state-of-the-art network, a specific one, with maybe convolutions of this or that striding or padding of a particular kind, how come he observes that the performance changes by a certain amount? And to me, that's an example. So it's hard to say at this point whether that question is too microscopic or not, because that's it could turn out to be actually maybe he was getting at a more general phenomenon. But some questions are too maybe microscopic. Like if I were to say in a material or some complicated system, ask you about what happens to that particular, say, system with those initial conditions, there's really nothing you can say about it other than simulating it, in which case I would just run the experiment on that particular problem. So part of the heart of this is to kind of tease out the right questions after at least the big open ones have been answered. And then maybe the second point theoretically, or how we've proceeded in the theoretical sciences, specifically in physics, has often been to take limits of problems with the hope of solving them exactly or being able to say something about them and to perturb away from that. And that's been the hallmark of the success of perturbation theory in physics. And I want to say that at least until you both do this, the take the limit, and you also do the perturbation theory, then it's then you haven't fully kind of exhausted what you can do with this. And until you do that, and we'll come back to this at the very end of the talk, I think it's too early to say whether a particular theoretical solution is useful or not. So which limit do we want to start with? This talk will be all about a limit that I think people now kind of understand a lot better. It's the fixed depth, but depth can be an arbitrary large width limit of neural networks. There's one reason to do this is, of course, the mathematical simplification that arises when you treat a many-component system. Oftentimes, then, rather than think about the individual components of the system, say like the individual parameters, a simplification arises if you instead consider the distribution over such quantities, and you look at more collective effects, and there can be simplification there, just as there is in StatMech. But really, the main motivation also comes empirically from a number of papers over the years. These plots are taken from our paper, but certainly there was a lot of evidence accumulating in this direction empirically that wider networks tend to generalize better. And here, the experiments that I'm showing are for the most part, they're fixed depth networks, just increasing the width. You might observe a different phenomena if what you did was change the depth and the width in a more particular way, scaled together, which I think is an interesting experiment by itself. But these are experiments where the depth was fixed, and as you just increase the width, at least the best performing networks measured by the generalization gap tend to be the ones that are the widest. This is for a fully connected network. We have something similar for the convolutional case. So here the width is going to refer to the number of channels in a particular convolutional layer. And again, as you increase the number of channels, the test performance, here these are like 100% accurate training accuracy networks with 100% training accuracy, but the performance goes up, and similarly a plot just aggregated over many tens of thousands of networks as you increase the number of weights. And even further back, I personally was inspired by a lot of the work from Neeshupper et al., who also had made these plots now quite a while back now, just looking at the improvement in the performance as you increase the number of hidden units. So it's natural to ask what happens in the limit of infinite width. Now, maybe a second point is how much you can gain by changing your perspective, which again, now it's in hindsight, a lot of this is clear. But maybe thinking back a few years ago, I think the discussion in deep learning tended to be a lot about parameters, or just a very parametric space point of view. And it's become clear that maybe it's clearer to neuroscientists and physicists, but within deep learning, I think now the discussion has kind of shifted to talking more about functions, because in the end, that's what we care about. And in particular, thinking about this correspondence between classes of functions and distributions, say, over parameters and an architecture. And when we talk about functions, we could talk about the input-output function. We could talk about functions realized at intermediate layers. All of them, they're governed by certain differential equations, which we can try to solve or might simplify, or we might hope that they might simplify. But particularly for neural networks, the parameters don't really have a clear meaning. They weren't introduced to be interpretable. For one thing, there's quite a bit of symmetry, like permutation symmetries. There's high redundancy that comes about due to just the training process and particular kinds of data. And so shifting the perspective to function space, I think, can be valuable. And in particular, we're going to go in this direction, where I give you an architecture, I specify a distribution over parameters, and we're going to think about the distribution over input-output functions. So this is maybe the first example, now quite a bit old, due to Radford Neal from the mid-90s, in which we explore that direction from architecture, prior over parameters, to a prior over functions. So the setup is, let's say you have a single hidden layer fully connected network. You're given input x in r to the d. Parameters are the weights and biases of the input-output layers. And now I specify a prior over parameters, which is IID. And in this particular case, we're going to take them to be normal, but you can relax some of these conditions, as you'll see. The prior over the weights needs to be such, though, that the variance scales as 1 over the width that's coming in. So I call that n in, which in particular for W1, which is the output layer, we're going to take n to be infinity, so this is like 1 over infinity. It's decreasing in size as we take that limit. The biases, again, some of this can be relaxed, but let's take them to be normal. And these coefficients, the bias variance sigma squared b, and I've dropped the index there, sigma squared w, they're order 1 coefficients, which we're going to tune later, but they're going to stay within an order 1 regime. And so this is the computation that's done by the network. If you take n going to infinity, then you can apply the central limit theorem, and this output sum is just a sum over IID infinitely many random variables. And so the distribution on the output is governed by a Gaussian process. It's also helpful to note for an induction step that we'll use in the deep case that different hidden units will be independent, because we're going to continue applying this for the deep case. But the conclusion is that Z1 is governed by a GP, and I write that with these curly letters, with a mean and covariance function which we can calculate. Throughout this talk, the means of all of our GPs, at least at the level of the prior, are going to be mean 0, just because we took the parameters to have mean 0 priors as well. And all of the information content will be in this covariance function k1, which in this case it's just some function of xx prime, which I haven't written down. So this was known in the 90s for reasons that I don't know. I think the gap, nobody extended it to the deep case, or at least made the connection to Gaussian processes properly until like we did last year. Again, the setup is the same. And in this original paper, we didn't have, we had kind of a sequential argument, not a rigorous proof, but since then, others have given a rigorous proof that doesn't rely on a sequential argument, and we ourselves have also given a more rigorous statement of it. But again, the setup is the same. We choose a prior on parameters that is IID, and again, what's important is that the variance of the weights be scaled as 1 over n. That's something that's going to keep coming up throughout this talk. You do this iterative computation, and now we can use that induction step that I mentioned on the previous slide. If you imagine that you take the width of the hidden layers successively to infinity 1 by 1, starting from the input to the output, then you can imagine you could apply the central limit theorem at every step. And so Z is governed again by some GP with a covariance function, which I denote by k to the L. And it satisfies this relationship, where all I need to do is compute this expectation value of these phi's, given that the previous layer's pre-activations are governed by another GP with covariance function k to the L minus 1. And just notation-wise here, although I've already been using it, Z, so I let Z denote pre-activations. These are the things that go into the hidden units. L is, of course, the layer subscript. I is going to denote the hidden unit, or later channel for the convolutional case. So this is the recursion relationship that we have. And in terms of a map of what's going on, so this is the computation that's happening in the neural network iteratively. And in the space of kernels, there's some computation that's happening from the input to the output as well. So K0 is just this base case. It's before you apply any nonlinearity, it's the covariance function you would have computed from the data. So it just involves an inner product between x and x prime. And as you continue forwards in the network, you map K0 to K0 to K1, and so on via this map that I'm going to call C, where C has a dependence on the nonlinearity, but is otherwise something that's it has no other dependencies. And the hyperparameters here, the weight and bias variances, have all been factored out. And so this is what you get as n goes to infinity. This is kind of the map in the infinite width limit, but you can imagine that if you were to move away from the infinite width limit as well, that maybe there would be higher moments that you would need to track, and you would keep track of those. They might satisfy their own recursion relationships. It might become more complicated in terms of the combinations, but this is kind of how you move away from the infinite width limit. So let's look more closely at this recursion relationship. So I will say that those types of kernels had been constructed before, not really making the connection to Gaussian processes. So these are, there may be generalizations of a class of compositional kernels that I've seen in a paper by Cho and Saul from 2009. And so it turns out like for particular nonlinearities, you can also compute a closed form expression for these kernel functions. So for instance, for ReLU, this is the actual expression for the recursion relationship. And here's maybe a 1D visualization of that. So this is a plot where I'm showing k of theta. Theta is the angle between x and x prime. For x and x prime fixed to have some particular norm. And this is as I vary theta. And also as I vary depth. So for the depth 0 case, where you have no nonlinearity, basically you just expect a cosine plot because you have x dot x prime for your covariance function. So that's this very first curve. And then as you start to pass this through a deeper and deeper network, you see that the curve will start to bend, it'll start to flatten, and we'll talk about why it'll flatten in just a minute, but this is sort of the structure of it, at least in this like 1D kind of visualization, it doesn't have a lot of structure. And here are samples from a Gaussian process neural network when that network has depth 10. Okay, so now this is a little bit of a detour to talk about basically the effects of these recursion relationships as you take the depth to be infinite. And this actually kind of predates a little bit in these papers by Poole et al., Schoenholz et al., and even earlier work. This predates the Gaussian process correspondence a little bit. But you could imagine that these recursion relationships, if you were to, they kind of could be used as a heuristic or a proxy for what a good initialization would be, in the sense that it turns out for these sorts of architectures, all of the ones that we'll consider, you don't really have a strong signal as you propagate these with depth from the input to the output because you don't have direct connections or you're not scaling up those direct connections enough. And so what happens as you iterate this forward with depth is that you start to lose the structure of the data, the covariance initially that you had initially between x and x prime. And so what happens in these, most of the architectures that have been considered is that you approach a boring fixed point. And these are the fixed point. You approach them at different rates depending on how you set the hyperparameters, so how you choose sigma b, sigma w, and phi. And you want to choose, you might imagine that in order, one proxy for good training would be that you want to choose your hyperparameters so that you retain as much of the structure of the input as possible for as long as possible. So if you're losing that certain structure and let's say at a characteristic depth scale, you've lost a certain amount of that structure, a network that's of order of that depth may have a hard time training. That's one hypothesis you might have. And that kind of turns out to be the case. These papers explored that, and I'll show you more results for the convolutional case. But here's... Mm-hmm.
I'm a little confused. Is the thing that you're saying the opposite of what Kishki said in the topic on the information model? Like, was he, like, is that fair?
Can you repeat the statement?
I might just be not. Okay, sorry.
Well, you want to maintain the structure that you had in the shallow layer. So you don't necessarily want to keep x dot x prime because you want to pass it through a nonlinearity and have a more interesting covariance function. But on the other hand, if you were to just keep iterating that for depth going to infinity, you, as you see here, I mean, you're getting a flatter and flatter covariance function, and it's going to become, at some point you hit a numerical bottleneck also. So if you were to look at the mean predictions that come from these sorts of more pathological kernels, you wouldn't get good numbers out of it. You wouldn't get good variance estimates. So that's sort of one way to look at it. This is just a 1D slice of it. So if you imagine x and x prime are rotated through some angle theta, yeah. Yeah. Yeah, so the norms are not so important, and you can even set the norms of like x and x prime to be at the fixed point values, as we'll see, but it's mostly the correlation between them or the angle that's important. So back to this. So this is just like a hypothesis you might have. It's something that you expect to hold in the infinite width limit, and now you're also going to use it for finite width networks, kind of as a heuristic for how to initialize very deep networks. Because without this, I don't think there aren't very many proposals out there in the literature for how to systematically initialize neural networks that are very deep. And this is like one hypothesis you would have coming from the infinite width limit. So let's look at this recursion relationship, just rewriting the, just changing notation a little bit to make a connection with these other papers. So if you imagine looking at this covariance function, basically in terms of two variables. One is just the covariance function evaluated on the same set of inputs, so the xx part of this, and then also the xx prime part of this, but we're going to look at the correlation and not the covariance. So normalized in this way. Well, let's look at the case of the same input xx. This is basically a rewriting of this recursion relationship where what you see is that to evaluate q to the L, I just have to do this integral. This is an integral with a standard Gaussian measure of the square of the nonlinearity. And if it turns out that if you were to, for most of the nonlinearities that we've considered, again, these have fixed point values, which you can solve for. So imagine if you solved the equation q star equals this with q star substituted back in, that's some equation which gives you a fixed point value for q star. This is the equation that would give you c. Now, if you substitute in c equals 1, you see that it's automatically it's going to degenerate into this equation. So c equals 1 is always a fixed point, but whether or not it's stable depends on your choice of hyperparameters. And so the stability of that fixed point is governed by evaluating this quantity, this derivative, which I'm going to call chi. Again, it's a function of these weight and bias variances. And it's this equation right here. Again, this is a standard Gaussian measure, and it involves the derivative of the nonlinearity. So based on this previous work, there are, you can kind of characterize the 2D phase diagram of the weight and bias variances into these different phases depending on whether the c equals 1 fixed point is stable or not. And there's a transition in between them when chi equals 1. But historically, this chi less than 1 part of the phase diagram has been called the ordered phase. You can think of it kind of as a phase in which the bias term dominates the signal propagation. So when the bias variance is large enough, you're just adding in a constant signal regardless of the input x or x prime, and that's why they're all collapsing to the same value. In this other regime, when the weight variance dominates, you're just multiplying in different random matrix at every layer, and so you're randomizing the inputs and kind of decorrelating them. And so what happens on this side is that you have fixed point values c star, and I should say this is particular to tanh. You would get a different phase diagram for a different nonlinearity, but there are different fixed points c star all throughout here that all have different values. And again, this transition happens when chi equals 1. Now, so far that has been just a discussion of the forward propagation. We were looking at this forward propagation from the covariance function, that recursion relationship that I wrote down. But you can also look at kind of the recursion relationship coming up in backprop. And so if you were to imagine looking at the norm of these pre-activation gradients, which is related to the weight to the gradients with respect to the weights, of course, you could write down a recursion relationship there. If you make an additional assumption, which it seems to actually turn out to be true in the infinite width limit, that the forward and backward parts of the signal actually are independent, then what you see here is that this part of that backprop is actually giving you kind of the same integral that you have over here. And so what governs the strength of the norm of the gradient as you move from the back of the network to the front is the value of chi. So if chi is less than 1, these gradients are vanishing. If chi is larger than 1, they're exploding. And so you can also give a correspondence between what the phases as identified by the forward propagation are and how they relate to the back propagation. So this is all older work by other people, not myself. But I want to relate it to the fact that these recursion relationships, which here are going to be for the kernels that I've written down, but you could imagine doing the same thing for the neural tangent kernel, which we'll get to at the very end of the talk. All of these are recursion relationships which you could use as a proxy for initializing neural networks. So we, in particular, looked at the case of the convolutional kernel, which I'll also come back to in the Gaussian process correspondence. And so these results are for that case. I should mention, also most importantly, is that once you identify the fixed point values, you can linearize about them and then get these effective depth scales that I mentioned, which govern the rate of convergence to the fixed point. So epsilon is kind of the deviation from the fixed point value. And it's going to 0 at an exponential rate, at least for this case of the tanh nonlinearity in the 2 phases that I showed. And there are depth scales C sub q and C sub c that are governing that. C sub q is for this q fixed point, and C is for the correlation fixed point. It turns out that C sub q often is small numerically, and so you approach the q star fixed point quite rapidly. But C sub c, the depth scale for the correlation, actually diverges at this transition. And so that means that the closer you sit to this line, you actually have, for many more layers, a propagation of the correlation that you kind of originally had in the inputs that you might want to retain. So the idea is try to initialize a network as close as possible to this line, and in particular, given a depth d network, there's a region outside of far enough away from this critical line where you might expect that you're not able to train. And you see that here. So these are different time slices during training, but the y-axis is depth. The x-axis is a sweep of weight variance. And so what we're doing here is taking a cut for fixed bias variance, just sweeping the weight variance, where we know this depth scale diverges at this transition, but is finite and vanishing rapidly away from it. And you see indeed that if you looked at the train accuracy, which is the more red regions and black is untrainable, what you would see is that as you approach that critical line, as you sweep along this one-dimensional cut, as you sweep weight variance, that you're able to train networks that are very deep. Whereas if you were sitting somewhere out here, you might not have any chance of being able to train. So there's a relationship between the depth and the effective length scale that you have that depends on your choice of hyperparameters. I will say also that for the particular case of, so this is also this sort of general behavior you also see, of course, for the fully connected case. For the conv case, I will say that one difference is, of course, as you'll see in a bit, that you need to keep track of spatial structure as well in this covariance function. And one thing that happens when you study these fixed points and the linearization about them is that what happens with a very deep CNN, so these are ultra deep, like thousands of layers deep, is that it starts to lose different Fourier modes of propagation at different rates. And so such a very deep CNN actually at very, starts to look more like a fully connected network before it becomes completely degenerate. So the mode of propagation that it keeps the longest is the one that's kind of like the DC component, like a fully connected network would. And you see that here in terms of, this is training or test accuracy as a function of time. So dashed lines are train, solid lines are test. And all of these networks train to 100% accuracy. So these are all conv nets. But depending on the depth, so sweeping from 32 to thousands of layers deep, the test accuracy starts to go down and starts to approach that of the fully connected network, which is kind of depicting that degeneracy. Okay, so now that was maybe just a side, a tangent on signal propagation, but to come back to the Gaussian process correspondence, So what we had up till this point was a characterization of the prior over functions at initialization. And up to this point, this is kind of like where a lot of theory discussion has been in the past in terms of let's study random networks. We study them at init, but we don't know what happens after any kind of training. And that was maybe one hard part of the problem. But the nice thing here is that kind of for free, having mapped it over to a Gaussian process, you can also say something about training. In this case, what we had done at this point was just Bayesian inference. But Bayesian inference with a GP prior is quite easy. It just amounts to, if you use MSE loss, it just amounts to doing a bunch of Gaussian integrals. And so you can get the exact predictive posterior distribution. So this is the distribution on the model output Z star given a test point X star and data set D. And it's a normal distribution given by this mean and variance function. And these are quantities that you compute given the targets on the training set Y, this covariance matrix that you constructed from the covariance function on the data set D. You need to do a matrix inversion, but it's just linear algebra that you do. And so that you kind of get for free now that you've mapped it over. So I want to go through some of the experiments from our original work, which is now, again, as I mentioned, a bit outdated, but were nonetheless very suggestive and I think interesting. So what we did, given this Bayesian inference using this NNGP, was to compare the performance of it, basically doing the linear algebra, against finite width deep networks that were trained with some variant of gradient descent. And because we wanted to keep everything within MSE and do an exact comparison without any approximations, we treated classification as a regression task on one-hot targets on these two data sets. So these architectures are all fully connected. We vary the nonlinearity. We also hyperparameter optimize them, so the weight and bias variances are scanned, and also importantly, the learning rate is scanned. And so that's kind of what I'm going to show you. The kernel computation, so we either do it in closed form, for instance, for ReLU, we have the exact analytic expressions, or for nonlinearities where we don't have the exact integrals, you can do numerical interpolation, and we do the Bayesian inference exactly by doing the inversion on that n by n matrix, where n is the size of the training data set. So this is kind of what we found. In each row, you see a data set and the size of the training set, and then for ReLU and Tanch, the best performing models. Neural network is the one denoted NN, GP is the Gaussian process, and these are the hyperparameters of the best models. But across the board, kind of in almost all cases, you sort of see that the GP does better or basically as well as the neural network, even though these are fully connected networks trained with MSE loss, where learning rate is also tuned. And even on the full data set at CFAR and MNIST, you see that the GP for this fully connected set, fully connected network does quite well, at least in relation to the neural network. This is maybe a different view. Quite, in terms of for the GP, yes, yeah. So it's costly, and it's not. You could take two kind of points of view. You could either, this is maybe interesting if you wanted to use Gaussian processes as a method. It was also suggestive at the time that we did that there was maybe some deeper connection between all of them, and that's kind of the angle that I'm going to take here. So we're not going to do any like clever GP approximations to speed it up. We're in all of these experiments, they're kind of just done exactly. No, they're the infinite width kernels, yeah. Yes. Yeah, so that will be towards the end of the talk. The difference in a nutshell is that the neural tangent kernel is this plus some other terms, and those other terms come from all of the gradients from the earlier layers. So the neural tangent kernel is this, which I'm going to refer to as the NNGP plus some additive an additive contribution from another kernel. And I guess this will take away from the end of my talk, but whether or not so at the time that we wrote this, we weren't aware of NTK, and this is kind of like leading up to that. But now, in hindsight, you can go back to all of those cases for different architectures and talk about the difference between this kernel and that one, and whether or not the performance difference matters. I'll try to argue by the end will depend on the architecture. Okay, so this is maybe a different point of view on the performance. This is connecting it now to these phase diagrams that I showed for signal propagation. So these show kind of the regions in bias variance and weight variance, this 2D plane phase diagram where the networks do quite well. So the purple, the more purple it is, the higher the test accuracy. And then going from left to right, we're just increasing the depth. So over here, it's depth 1, and out here, it's depth 100. And what you see is that the high test accuracy areas tend to concentrate along these lines. These are exactly the lines that you would have predicted from studying these fixed points. This is the one that I showed you earlier for tanh, and you can calculate what that is for ReLU as well, and you see that it aligns well. So again, this is a reflection of the fact that for all of these architectures, you're not sending in the input information in such a way so that you retain interesting structure. You could imagine maybe there's a way to beat this by having skip connections that perhaps scale in a particular way with depth so that you kind of push more of the signal from the input into deeper layers. But the sorts of architectures we're going to look at here don't have that property, so they all have boring fixed points. And this is maybe the final look at sort of the same data, which is looking at accuracy as a function of training data set size, but also increasing the width of the finite width neural networks that are trained with gradient descent, and then comparing them to the performance of the NNGP. And again, the general trend, which I showed you earlier anyway, was that as you increase the width, the performance of these networks tends to go up. But in particular, they're getting kind of close or ballparkish close to the NNGP, which is the black curves, and actually in this fully connected case tends to be quite good across a range of data set sizes. So what are we left with, or what were we left with at the writing of this paper? The manner in which we commonly initialize neural networks yields an especially simple description of the network in function space. So you have this simple class, you can characterize it analytically very easily. Maybe a different question that's worth thinking about are there other priors we ought to be considering for tasks of interest? So is this Gaussian process limit actually a good one? Going back to Neil's earlier paper, he kind of entertains the idea of other priors, maybe hierarchical priors or priors where you break the central limit theorem explicitly. So I think given that all of our many of the architectures that we're dealing with in practice all have kind of the same limit because we initialize always the same way, it's worth maybe revisiting this question for at least different tasks that we might be interested in. The other takeaway was that at least there was one form of inference or training that resulted in a very simple description, which was, in this case, it was Bayesian, but it begs the question, could there be other forms of training that also yield rather simple descriptions in this limit? And then performance-wise, at least for this fully connected case, there didn't seem to be a lot of benefit from this kind of special bias of SGD, or the fact that we believe that SGD is quite good. At least it wasn't shining in this particular case relative to Bayesian inference. Now, that is because we're dealing with fully connected networks and also MSE loss, and we know in practice we're often dealing with cross entropy. So that's a different case that we can't really consider here, or we didn't consider here, because we didn't we wouldn't have been able to implement the inference exactly. But it's at least worth stating that any paper that kind of, or any sort of inquiry that you would have into such networks, in theory papers when we look at fully connected networks with MSE loss and we compare them to other things, it's worth maybe considering the fact that these networks may essentially be kind of close to networks that are trained in a Bayesian way, or may not be highlighting kind of this special gains that we have from SGD in real state-of-the-art networks. So we kind of need maybe more of a distinction to be careful when we talk about, when we look at empirical data and we're trying to also match theory and experiment, to be careful about what we're talking about exactly and whether we're kind of in this regime where we believe deep learning really shines. Because the takeaway here is maybe that this might not be one of them. And nonetheless, these networks are used maybe not in state-of-the-art cases, but in scientific applications or maybe small data set applications, they're used quite a bit. And so it's maybe worth taking that into account. So this was the story with fully connected networks. You can play the same game with any other model where you take some relevant dimension to be infinite. And we're going to play that game with the convolutional case. So the setup here is just for simplicity of notation, is just 1D with periodic boundary conditions. So to introduce the notation, the network is performing this computation iteratively, and now L, of course, is the depth. I is the channel index, which we're going to take the number of channels to be infinite. Alpha is the extra ingredient, which is just the spatial index. And of course, there's still the input x. And here we have these n channels. 2k plus 1 is the size of the filter. So that also appears in this normalization here. And this is the way that we do convolutions in terms of the combination of the spatial indices. So again, you have an IID prior over parameters. And once again, you scale the variance as 1 over the width, which you're going to take to be infinite. And we have a rigorous statement in the paper that as n goes to infinity, the distribution on the output becomes a Gaussian process. And this earlier work that I showed you about signal propagation for CNNs also considers basically this convolutional kernel iterated many times. So what is this convolutional kernel, or the covariance function for the convolutional case? It's this function here, where now we have the indices alpha, alpha prime, also the spatial indices that came from x and x prime propagated through. And looking at this, you see that it reduces to this sort of expression where we're summing over these indices beta. Beta has some width to it, which is of size 2k plus 1. So the only generalization here is that this map C, which was propagating your kernel function forward, now just has these spatial indices, which you also need to keep track of. But otherwise, it's a 2D integral that you, again, do against a Gaussian over here. Now, CNNs have many more architectural design choices. What I was talking about here and what we've considered for simplicity is basically just having L layers of just pure convolutions propagated forward, and then we're going to look at 2 different terminations to see how that changes the final covariance function. But you can imagine, I mean, there is a much richer class here that we haven't really explored, where you could use different striding and skip connections and that sort of thing. So let's look at 2 different kinds of termination. The first one is just what I would call a vectorization. So what you do is you take the final signal z to the L after L layers of convolution, you just flatten it, pass it through nonlinearity, and then combine with a final dense layer. So this dense layer is now combining over indices that's of size n times d. D is the size of the image, so the spatial extent of the image. N is the number of channels, and you're just flattening it, passing it through, and combining it with this final affine transformation. And if you compute the covariance function for that case, what you see is basically that what will be imposed, basically by all of these being IID, is that the j and j prime indices will have to be the same. And what that will mean is you'll only extract the diagonal spatial elements of this of whatever you got from the output of the convolutional case. And so, although you had convolutions within the network, with this choice of termination, you lost covariances between different spatial locations. And this is, in effect, losing the benefits of weight tying, because a locally connected network that would have had local filters but didn't have any weight tying, would have resulted in the same sort of covariance function. And so that's sort of what this case gives you. There's a different class of maybe terminations where what you do is first is pass through the nonlinearity, but also project onto some vector h in the spatial dimension. So combine the spatial indices in some way first, and then pass through a nonlinear, combine it with an affine transformation at the very end. And that covariance function, what it gives you is basically a mixing between different alpha primes. And you can consider various examples of this. So if this final vector just sums up all the alpha indices with the same weight, it's doing global average pooling. And so what you get over here is, this is the sort of covariance function you would get from global average pooling, where you sum over all different spatial locations together. You're not just keeping the diagonal components. And a different case, which is not a particularly good one, but had been considered kind of in recent work, is this one where you just select a particular pixel as well, and we compare to that. But the real one that we want to look at is global average pooling, because we think you would expect that covariance function does well and maybe better than the vectorized case, and indeed that's true. So here's a plot of various cases of these GPs for a small training data set as you increase the depth, and this is plotting the test accuracy. So let's look at, if you look at the brown and the green, the brown is the fully connected GP that I showed you earlier. The green one is the CNN GP just with vectorization, so no global average pooling. It's the one that you would have gotten from just local weights, but no weight tying. You see that still there is some benefit here in this gap between the green and the brown lines from local filters or weight, local filters, but no weight tying. There's another case where you just extract the center pixel, and that performs very poorly when the network is not as deep. But as the network becomes deeper, the center pixel itself starts to acquire a lot of information because you get mixing of the different spatial information in the receptive fields. So at some point, that CNN GP also picks up in performance. And then, as you might have guessed, the very best one is the one with global average pooling. For these particular experiments, we didn't have, I'm not showing you the exact CNN GP with pooling, but a Monte Carlo estimate. So this is one where you take a finite width network and you sample it repeatedly to get to construct an approximation to the kernel function in that way, but that one performs the best. Here's a different take on some of the same data. So this is considering two different networks, locally connected networks, CNNs, as you increase the number of channels, comparing the performance of the neural network and the Gaussian process. And again, as we saw with the fully connected case, in a lot of the cases, this is kind of like a generic choice of hyperparameters or initializations, but choosing kind of the best learning rate and other parameters, the neural network performance tends to approach that of the GP for this, at least this choice of small data set sizes. But then if you were to look at kind of the performance on the full data set, really tuning all the hyperparameters together. So this is the generic picture, but there are particular choices of hyperparameters that are quite good, and that basically results in the CNN, the finite width networks that are trained with SGD outperforming the conv GPs. And so you see that here. Let's go maybe from bottom to up. So this is showing you the test error on CFAR10, and this is basically the same fully connected data that I showed you earlier. This was the number from our original paper, and kind of repeating the experiment, the fully connected finite width networks kind of do a little bit worse, and actually the GP numbers went up when we redid them here. So you see again that same trend where the GP does better than the finite width network trained with SGD. But for the conv case, this is the number for, so I should say this block is comparing CNNs that only have the vectorization at the very end. So the neural networks just have a final dense layer with no average pooling, and the CNN GP does as well. So you see that a CNN at small learning rate, or any learning rate with a particular choice of nonlinearity, performs in the same ballpark as the CNN GP. But then if you have a CNN with ReLU and large learning rate, it does quite a bit better. And then also, depending on whether you filter for 100% train accuracy or not, you can get the numbers to kind of move around. And at the time that we did this, we didn't have we weren't able to scale up the experiments for the CNN GP with pooling to the full data set size, because here you have this additional spatial index that you have to keep track of along the way. But then we kind of expect, and more recent results studying the NTK have kind of suggested that there is still a gap between the finite width CNN trained with SGD and the GP version of it. But here you can see that it happened, for us it happens at the largest learning rates with a particular choice of nonlinearity. And again, they were not observed in the fully connected case. Questions for this part? Okay. So the very last part of my talk will now be about the new developments coming from thinking about gradient descent and not just Bayesian inference. And I'll kind of interchange between gradient flow and gradient descent. But one of the nice kind of perspectives that came from thinking about what happens with gradient descent in infinite width networks is sort of, again, this function space perspective, which I've summarized here, which is that we've mostly been thinking about, the differential equation that governs the parameters because of our very parametric point of view on networks. But if you look at the differential equation that governs the function, then basically there's this quantity here, which is the neural tangent kernel in a general sense as a dynamical variable that kind of enters on a special footing. So this is kind of like the esteemed dynamical variable that we should all be thinking about, and whether or not it's fixed, it's the study of it during the course of training and maybe in other limits is what's interesting. So that's a very nice compact way to kind of summarize the thing that we actually care about, although the thing that we actually touch when we train the network is this equation up here. Now, the nice result that appeared due to Jacot et al. And then many others since then who have kind of refined the theorems and the statements is that in this infinite width limit, this theta function is frozen, of course, and this is the neural tangent kernel. There's maybe a nice kind of back of the envelope. I mean, I don't know how familiar you are with the details of it, but it's easy to kind of see at least back of the envelope with estimates why the neural tangent kernel is frozen. You could do it in standard parameterization if you wanted to, which is how we usually initialize, in that we take that 1/n factor from the variance and actually put it in the weights. But you could do as they did in the paper, which is use NTK parameterization, where the weights themselves are order 1 quantities, but you put the factors of 1/n explicitly out in the model, or 1/√n explicitly in the model definition. The difference between these two, if you have enough learning rates for different layers, you can kind of map one to the other. But another difference is that if you were to have a single learning rate for the entire network, you would need to maybe adjust the learning rate with width in these two cases differently. So NTK parameterization is nice because as you increase the width, the learning rate stays in order 1 quantity. You don't have to change the range over which you sweep it. And that's because that learning rate is set by the max eigenvalue of the neural tangent kernel, which is also kind of converging to something that's fixed. And if you use standard parameterization, you would have to adjust for that. So to see that the NTK is frozen, you can do a back of the envelope initial estimate of what the expectation of the gradients for any internal variable would be, whether these are parameters or whether they're activation functions that are internal to the network at any hidden layer. This is the case for a single hidden layer. I've written it as 1 over root n, but if you do a deeper network, you might get 1 over n for the intermediate cases, and 1 over root n for the input-outputs. But if you were to look at theta, you would see that it's an order 1 quantity. And then if you were to write out d theta dt, basically originating from these scalings here, you would see that it vanishes as n goes to infinity. And if you were to, for instance, evaluate the expectation value just set init. And so given that the initial values scale in this way, if you imagined you ran gradient descent for an order 1 time, these scalings would kind of persist. And again, you would think the neural tangent kernel would be frozen. Now, what's non-trivial is, of course, you need to run it for a certain amount of time that might scale with n. And that's the non-trivial, one of the, among a number of non-trivial aspects of the proof is how that time scale changes with n. So you do need a more rigorous version of that, which I'm not presenting here. But this is kind of a back of the envelope look at it. And theta here is defined as a contraction over these gradients. But again, the last layer gradients are just up to kind of scalar coefficients, just the NNGP kernel that we've been talking about up to now, and then everything due to the earlier layers, which you can characterize involving this product of kernel functions that involve derivatives of the nonlinearity as well as thetas from previous layers, is encoded over here. Okay, so that's the result from NTK. We kind of worked on something that has a little bit of overlap with that, in that we were looking at what dynamics occurs in parameter space, or what kind of model realizes these dynamics. And kind of the answer is sort of simpler, as you would expect, since you map over to a kernel, to evolution with a fixed kernel in the infinite width limit. Then what you effectively have is a model, or a model in which the trainable parameters, a model in which you basically have an affine combination of the trainable parameters. And so one way to realize that, or to see that explicitly, is if you imagine Taylor expanding the function at initialization with respect to these parameters. What you would get here are these gradients evaluated at init. And indeed, these are the differential equations that you would get for such a model. And you can show that the distance kind of between this linearized function and the nonlinear model goes to 0 as the width goes to infinity. So indeed, this is kind of the model that realizes those dynamics. And so although the function space kind of evolution equations were known for NTK, what you get in addition in this case is an evolution equation also for the parameters of the network. Now, every parameter changes a vanishingly small amount in the infinite width limit, but the idea is that all of them collectively kind of conspire to give you a change in the very final output value of the network. So an order 1 change in Z.
So, does the kernel being frozen correspond to the gradient being constant in the parameter space?
The gradient of the logits with respect to the parameters, yes. This is not the gradient of the loss with respect to the parameters.
I see. So the gradient of loss is not constant.
No, because it's controlled by the error term, like the DLDZ.
Is
So,
the direction constant and the magnitude changes? Or?
well, like, so, like, what's controlling the dynamics is this term, like the residual term. So the gradient dz d theta is frozen, but dl dz is dynamical. Yeah, so this is what you gain in addition, kind of in parameter space. And then we did some empirical work kind of comparing how well this linearized model approximates the dynamics of a nonlinear network for various cases. And before I show you that, this is just a check that everything works out as you expect, basically that the change in the parameters as width goes to infinity is vanishing, and it vanishes at either 1 over n or 1 over root n, depending on which layer you're looking at. Here's a check that the kernel function doesn't change from its, or does not change from its initial value as n goes to infinity, and this is something similar just for the last layer part of the neural tangent kernel, which is the NNGP kernel. So all of them are going to 0 as n goes to infinity. And I should say, so this kind of dynamics is something that you expect up to a critical learning rate that's set by the eigenvalues of the NTK. So you don't necessarily need continuous time dynamics. You could do discrete gradient descent, but there's a learning rate up to which it holds. Given these exact kind of dynamics that you have both in z and in theta, you could see that what you have is basically just an affine transformation of the initial value, z of x, at time 0. And so given that we know that the prior is governed by a Gaussian process, that's some Gaussian random variable, you have a Gaussian random variable, you do an affine transformation, you end up with still a Gaussian random variable. And so the distribution of the model output at any time, given some test point x star, is still some Gaussian with a mean and a variance that you can write down explicitly from that formula. And what you see here is basically how it's different from the Bayesian inference results coming from the NNGP. So for the mean prediction, what you would have had here, let's say if you considered the infinite time value, is kind of the same expression, but with the theta naughts, with k substituted for theta naught, because that's the only kernel that's relevant there. And here you have a more complicated expression for the variance, but again, it would degenerate into that other case if you were only training the last layer of the network. These are some more numerical comparisons between the predictive distribution of the NNGP, NTK, and some ensemble, an ensemble of size 100 of random networks of finite width during the course of training. So what you see here are like 2 training points with certain values and a 1D kind of interpolation between them, and then the initial values of the GPs. And during the course of training, you see that, well, the means of the GPs are starting to narrow in on the target values, and there's some variance away from the training points, which is this variance here, either for NTK or for NNGP. And you see that there's actually a slightly better match in the variance between the NNGP and the finite width neural networks, in that, like, between NTK and the finite width neural network, so between the blue and the black. And that's because we know the blue is actually the right description of what's happening with gradient descent as n goes to infinity. So they're slightly different. But in terms of whether or not the mean predictions are different, that will depend on architecture. So you could go back and numerically or theoretically try to capture what the difference is between theta and k, kind of in the spectrum and in the eigenvectors and for different architectures, and kind of understand what this difference between Bayesian inference and gradient descent actually is. Here's some more empirical results, again comparing the actual dynamics of a neural network with the linearized model as a function of time. This is a case where we train the linearized model with discrete gradient descent, with momentum and cross entropy loss on full MNIST. And again, you see a pretty decent match. So you actually get better matching in the loss and the accuracy than you do in the individual values of the test of the function and the weights. So here you start to see these differences between the two at long times, but nonetheless a decent kind of agreement between them in the loss and the accuracy, despite this being the full data set, which I think is interesting. And here's a result for wide ResNet, or kind of a simplified wide ResNet, which is pretty wide. It has channel size 1024. This is trained on full CFAR 10, And again, you start to see this discrepancy between the linearized and nonlinear model at late times. But in this case, it's kind of out to, let's say, about 70 or 80% train accuracy. The linearized model is still kind of describing the dynamics reasonably well. This is a network that has skip connections. It has batch norm in it. And nonetheless, there's relatively decent agreement between the two. Here are some more numerical results looking at the logit deviation for cross-entropy loss, where you're going to get pretty large deviations, or the difference is going to hurt you more than with MSE. But you see that at least as you sweep width from size 32 to up to about 4,000, that disagreement between the linearized model and the nonlinear one gets pushed out to later times, as you would expect. And finally, this is showing the root mean squared error between the function that's learned for the linearized model versus the nonlinear one as you sweep width and as you sweep the data set size. So the root mean squared error is smaller as the width increases. It's going to go to 0 as you expect, but you see that the error increases as you increase the data set size. And this is kind of the thing that puts you away from the infinite width limit is how large is the data set size compared to width. I think at the moment, as far as I understand, theoretically, people are still kind of investigating exactly, other people are investigating exactly when that crossover really happens. So how wide do you really need to be compared to the data set size so that you're actually in the NTK regime, or at what time scale do you start to see these deviations kind of set in? And understanding that better kind of as a function of all the other hyperparameters, I think is still a bit open. And so that kind of concludes that part of the discussion. These are just some closing remarks. Kind of the takeaway is that these kernels, whether it's NNGP or it's NTK, how well they do or how they compare to each other depends on the architecture. And also, it highlights maybe the importance of hyperparameter tuning, or the fact that the very good, the real shining element of deep learning is in a particular hyperparameter regime. For instance, large learning rates or particular choices of nonlinearities, where you see the finite width network beats the Gaussian process performance. In terms of the picture that I've walked you through, or tried to walk you through, is that we kind of hit these X's along the way, although incorporating other work by other people in this box over here. But kind of we've, at least looking at the infinite width limit, we've kind of characterized what's happening in these 3 boxes. And there's still one box that I didn't tell you about and is open, which is the view of Bayesian inference in parameter space. So I think there are kind of 2, going back to the earliest point I made in the motivational slide. Now that we have an exactly solvable model, you want to perturb about that. So you don't want to throw the model, it's easy to shrug NTK, I think, off and say that it is not relevant to the dynamics of real networks, nonlinear networks. And I think we already saw evidence that that's the case. But there are many, depending on what property you're interested in, there is still some aspect of that prior or of that kernel that can carry over to the deep network. For instance, in how you choose initializations, or how signals kind of propagate, if you were going to have a heuristic for that. Or maybe certain aspects of generalization are still tied to properties of the kernel, even if the dynamics that you have for the nonlinear network are quite different. And then the study of the kernels in and of themselves could be interesting. But that's where I'll close.
We have time for some questions. Yasaman, oh, sorry.
Under this view, given that there's this imperceptible under this view, given that there's this infinitesimal movement in the parameter space to get you these large differences in the functional space. What do you think is needed to bring a Bayesian inference type? What do you think is needed to bring a Bayesian inference type of idea to the parameter space where you have this really kind of dense representation?
To solve this problem, you
Yeah.
mean, that box? So I kind of have collaborators who are thinking about this problem, so I won't say much. I will say that there is one case where you kind of recover a similar solution, at least in terms of what the computed function is. A parameter space solution which gives this to you, which is just training of the last layer of a neural network. So now that by itself is not enough to tell you what's happening in parameter space, but it might give you, kind of suggest a starting point for that.
Thank you.
Can I ask a really simple question, just about the beginning of your talk, the Gaussian processes part? If you just have a function from R to R, can you draw the graph of the typical starting function?
Mm-hmm. So that was the 1D plot that I showed at the very beginning. It was like scalar x and scalar output. Like these are samples from that Gaussian process.
I see. So like when I start, I might look like that green.
Yeah.
Oh, I understand. Thank you.
Questions? All right, let's thank Yasaman one more time.